Hi, welcome back to Classical Mechanics by Unify Physics. Let's continue our discussion into Lagrangian dynamics. Okay, in the last class, what we discussed is velocity-dependent potential. Today, we'll discuss the dissipation function. I think this will be the last session specifically on Lagrangian dynamics. All right, so this might be important problem-wise. Okay. Point of view of examinations, competitive examinations. We'll discuss the dissipation function and a little bit about friction, which is an example for situations where we use a dissipation function, and we'll do a couple of problems. Okay. Now, so if you remember it, right? So we said that we can write the Lagrange's equation. Okay, we can write the equation of motion in this particular form if all the forces are derivable from a potential. All right, in that case, it would be 0 here. Right, so we showed that we can write the Lagrange's equation in this form. Okay, dou L by dou Qj dot minus dou L by dou Qj. Generally, if all the forces are derivable from a potential. Okay, so maybe there are some forces which can be derived from a potential. So there are systems where there are systems that we need to deal with, for which some of the forces can be derived from a potential and some of them cannot be. Okay, in that case, we can always write the Lagrange's equation in this form. Okay, we'll write instead of 0, we'll have some generalized force components over here, which cannot be generally derived, which cannot be obtained from a potential. Okay, so L here, the Lagrangian here, it contains the potential of the conservative forces as before, and Qj here represents the forces that do not arise from potential, okay, that cannot be written in terms of a potential. So the most familiar cases where such situations arise is the case of frictional forces. Okay, you cannot write the frictional forces in terms of potential. All right, it's not a conservative force. Right. So in many cases that we'll discuss, the frictional forces are found to be proportional to the velocity. Okay, it's proportional to the velocity of the particle, and the direction is opposite to the movement. All right, so we can write F, the frictional force, the x component of it is proportional to Vx, and it's in the opposite direction, so it's minus, and there's a constant of proportionality Kx. All right, so usually in many cases that we will discuss, the frictional force is proportional to the velocity of the particle. Okay, and here this F stands for frictional forces. All right, and we are talking about the x component. Okay. Now, these kinds of frictional forces, if the frictional forces are of this kind, which are proportional to the velocity of the particle, then it can be derived from a function which we call as this curly f. It's known as the Rayleigh's dissipation function, and it's defined in this form. Okay, f equal to half sum over I kx Vx square plus ky Vy square plus kz Vz square. All right, and there's actually, this is for the ith particle, you sum over I to get the Rayleigh's dissipation function. Okay, it has a simple form. It is kx Vx square plus ky Vy square plus kz Vz square. All right, so in a general case, this coefficients, all right, kx, ky and kz could be different in a general case. Okay, it could be the same in all directions, or it could be different. This is the general form of the Rayleigh dissipation function. And remember, there's a 1 by 2 here. Okay, now it clearly follows that. Okay, since we said that the x component of the force, we said the x component of the frictional force. I am dropping the subscript f. All right, we are talking explicitly about frictional forces. All right, we said that this is equal to minus kx Vx, or generally f vector, the frictional forces, is given as minus, all right, let's say kx Vx x cap plus ky Vy y cap plus kz Vz z cap. All right, so this can be actually written. This force can actually be obtained by taking the derivative of the dissipation function with respect to the respective component of velocity, and there's a minus sign. Okay, there's an appropriate minus sign. So it's clear that if you take this derivative dou f by dou Vx, you will get the corresponding component of frictional force. All right, for example, here if you take dou f by dou Vx, all right, if you take dou x by dou Vx, you will get kx Vx. So minus dou f by dou Vx is minus kx Vx, which is exactly the x component of the frictional force in this particular case. Okay, so we can write it in this way. We denote a derivative which has three components. This is just one component, all right. So the y component would be dou f by dou vy, and the z component would be dou f by dou vz for the ith particle. Okay, so generally we can invent a new notation and write it as minus del vector f. Okay, so it's not del vector usual del vector, but it's del vector v. This means that this is the vector dou by dou vx, let's say x cap, plus y cap dou by dou vy, plus z cap dou by dou vz. Okay, this is what we mean by del vector v. All right. Okay, now what's the physical interpretation? All right, is this quantity relevant physically? What's the physical relevance of this particular quantity called the Rayleigh's dissipation function? All right, it can be seen by taking the work done, all right, by a small displacement, work done by the force through a small displacement dr vector. So that's f vector dot dr vector. That's the work done. Okay, so if there's a small displacement and if the force acting is f vector, then it is f vector dot dr vector. All right, so there's a minus sign there, of course, right? So this is the work done by the frictional force, or work done by the system against friction. All right, it's actually work done by the system against friction, not work done by friction, but work done by the system against friction. Okay, so this dr vector we can write as v vector dt, right? Because v vector is dr vector by dt. So dr vector can be written as v vector dt. So there's a scalar product there, right? So what do we get? What is this f vector? We said that we can write it. Okay, we said that we can write it in this form. F vector. This can be written as, we said that this has components. Okay, let's say minus kx vx x cap plus minus ky vy y cap plus kz vz z cap. All right, we said that f vector has this form, right here. This is the x component. All right, so there's a minus sign there. Now there's a minus sign which cancels with this, and when you take the scalar product with v vector, you get kx vx square plus ky vy square plus kz vz square. Okay, that's what we have here. And what is this? We see that when you calculate the work done, all right, by the system against friction, you get the Rayleigh's dissipation function multiplied by 2. Okay, if you have a 1 by 2 here, this is the Rayleigh's dissipation function. Am I right? For one particle. All right. So this is Rayleigh's dissipation function. So the interpretation, the physical relevance of Rayleigh's dissipation function is that it is twice the Rayleigh's dissipation function is the rate of energy dissipation due to friction. It's the rate of energy dissipation due to friction. All right, we say it's a rate of energy dissipation due to friction because there's a dt here. Okay, so if you divide this whole thing by dt, you will get twice the Rayleigh dissipation function. All right, so it's maybe useful to keep this in mind. Twice the Rayleigh dissipation function is the rate of energy dissipation due to friction. Okay. Now, so let's see how we can write down the Lagrange's equation now. All right, so let's talk about the components of generalized force from the dissipation function. Okay. So what we do is that we try to obtain the components of generalized force in terms of the dissipation function. Let's look at it. Okay. So we know that the general definition for generalized force is Qj is equal to f vector dot dou Ri by dou Qj. Okay, or simply Qj is equal to, for the ith particle. Okay, for the ith particle, it is f vector, or for a single particle, all right, f vector dou R vector by dou Qj. Right, this was the definition of generalized force. If you don't remember it, just go back to our previous lectures, and we have defined it like this over there. All right. So if you have a number of particles, you will have to take this for each particle and then sum over all I. Okay. So this is sum over I fi dot dou Ri vector by dou Qj. Okay, that's Qj. Right, but we said that this frictional forces, if we are talking about the frictional forces which are proportional to velocity, okay, then we said that we can write them in terms of the Rayleigh dissipation function in this way. Okay, it's dou Ri by dou Qj remains there. All right. Now we use the fact that dou Ri by dou qj is equal to dou ri dot, dou ri vector dot by dou qj dot. Okay, it's not very difficult to show this. We can show this right here. Okay, but that's what we do. So we write dou ri by dou qj as dou ri dot by dou qj dot. Okay. All right, and what do we have here? Finally, we get dou f by dou qj dot. All right, we get dou f by dou qj dot. All right, how do we get dou f by dou qj dot? There's a minus sign, of course, which comes from here. Why do we get dou f by dou qj dot? Okay, I'll prove this in a moment, or you can do it by yourself. It's something, it's not very difficult. Okay, but let's come to this. First, let's discuss this. All right, so we are talking about del v vector dot, this is a curly f, okay, dot dou ri vector dot divided by dou qj dot. Okay, all right, now this we can write as dou f by, okay, forget about this sum over I for a moment. All right, dou f by dou vx x cap plus dou f by dou vy y cap plus dou f by dou vz z cap. All right, that's this term. It's a vector. Dot dou ri vector dot divided by dou qj dot. What's that actually? It's actually dou vx. Okay, it's dou vx by dou qj dot. We have got an x cap here plus dou vy by dou qj dot, and we have got y cap plus dou vz by dou qj dot and a z cap. Right, now if you take the scalar product, these terms get combined and we get dou f by dou vx multiplied by dou vx. I'm just taking the first term out of it. The other terms are exactly similar. Dou f by dou vx by dou qj dot. Okay, this simply you can write as dou f by dou qj dot. Okay, all right, now yes, so this thing can be written as minus dou f by dou qj dot. Of course, you have to do it for all particles and sum over this I, but this dissipation function itself is defined as a sum over all the particles. All right, so that's that. So you can write qj as dou f by dou qj dot. Right, now once you have the generalized forces, you can put it in the form of the equation here. Just substitute qj is equal to minus dou f by dou qj dot. Okay, minus dou f by dou qj dot, and you can write the Lagrange equation in this form. So if there is a dissipation function, if there is a dissipation function, you cannot simply write d by dt of dou L by dou qj dot minus dou L by dou qj equal to 0. You will have an extra contribution, d by dt of dou L by dou qj dot minus dou L by dou qj plus dou f by dou qj dot is equal to 0. Right? So in order to get the equation of motion here, you will need two functions, okay, two scalar functions, the Lagrangian and the dissipation function. Right? So the basic idea is that you need to have some idea of what kind of dissipation is acting on the system, right, or what kind of dissipation is happening to the system, or what other influences are acting on the system. Right? That information has to be furnished in order to get the complete equation of motion. Right? An example is Stokes' law. Okay, so the sphere, for example, you might already be familiar with this. A sphere of radius a moving at a speed v in a medium of viscosity eta. Right, it experiences a frictional drag force which is given by f vector is equal to 6 pi eta a v vector. All right, so this is a standard thing that you have to remember, and clearly this is proportional to the velocity. Right, it's proportional to velocity, but we see that here kx, ky and kz are equal. Okay, it's 6 pi eta a, so in a way it's isotropic in that sense. All right, the kx is equal to ky is equal to kz is equal to 6 pi eta a, and clearly this can be written in terms of Rayleigh dissipation function, and you can get the equation of motion. All right, now coming back to this, right, if you are not very familiar with this thing, it's a good thing to look at the basics now and then. So let's do it here. So this thing. So if you take dou ri vector dot divided by dou qj dot, okay, this of course you can write as dou by dou qj dot of what is ri dot, it is dri by dt, okay, it's dri by dt. Now this is simply dou by dou qj dot. Okay. What's dri by dt? What's ri first of all? Ri is a function of, let's say, all the generalized coordinates, and it may have an explicit dependence on time. Okay, so its ri is generally a function of qj, all generalized coordinates, and time. Right? So we can use the chain rule. Okay, we can use the chain rule, which means that this is actually, let's say, q, there's an I here, so let's say qk, alright, so that we don't confuse. So let's drop this I for a moment, okay, that's of the ith particle, let's not complicate things. So let's drop this I for a moment, okay, so that's dou by dou qj dot of dou r by dou t can write as dou r vector by dou qk dot, alright. So this is the change, the time change in r vector due to the dependence of qk, or dependence of the coordinates on time, right? There are two contributions, all right, and then there's also dou r vector by dou t. Okay, so you might be wondering, of course there's a summation over k here because there are n generalized coordinates, so you have to sum over n equal to k equal to 1 to n, right, over all generalized coordinates, because these generalized coordinates generally depend on time. So the dependence of the generalized coordinates on time, right, that causes a time change r vector, and there can also be an explicit dependence. R vector can also have an explicit dependence on time. Okay, so that will be taken care of by this part. Okay, this is known as a chain rule. Okay. Now here I am using what's known as Einstein summation convention. Einstein summation convention. Okay, we'll be using it very often, all right, it simplifies things a lot. All right. So by Einstein summation convention we mean that repeated indices are summed over. Okay, so unless otherwise specified later on in our course, okay, if there are two indices which get repeated, we assume that they are automatically summed over. All right, so if you have something like this actually means that, because k is repeated, this actually means that in our convention, this actually means, actually in Einstein's convention, this means summation over k equal to 1 to n dou r vector by dou qk dot. Okay, so this is a nice thing by Einstein. So that's, in that way we can just drop the summation, we can save space here and time. Okay, but you just have to be careful and you'll get used to it, this Einstein summation convention. Now you have to take dou by dou qj dot of this thing. Alright, so you see that this dou r by dou qk, it cannot have any dependence on qj dot, because r by definition depends on qk. Alright, so if you take this, you have to, of course you have to take the product rule, but this dou r vector by dou qk cannot have any dependence on qk dot. So the only thing is you have got qk dot here. Alright, so you have to take partial derivative of qk dot with respect to qj dot. Okay, but this is 1 if qk dot, if k is equal to j, right? Because for example, if you have something like vx and you take the derivative with respect to vy, then it's 0. But if you take the partial derivative with respect to vx, dou by dou vx of vx, this is equal to 1, etc. Okay, so generally we can write dou r vector, dou by dou qj dot of qk dot, right? I'm just looking at this term. This you can write as delta jk. Okay, this you can write as delta jk. Delta jk is a Kronecker delta. It means that if j is equal to k, this is equal to 1. If j is not equal to k, this is equal to 0. Right? For obvious reasons. So this is a nice thing which can be used in manipulations. Kronecker delta. Okay, Kronecker delta, I'll repeat, it means that if the indices are equal, right, if j is equal to k, which means that if you take dou by dou qj dot of qj dot, that's equal to 1. Right, if they are not equal, it is 0. Okay, so this can be written as dou r vector by, okay, so this can be written as dou r vector by dou qk delta jk. plus this term is simply 0 because there are no qj dots in here. Alright, so dou by dou qj dot of dou r by dou t is equal to 0. Okay, there are no terms there, so I am not just writing it. Okay, this combination is directly 0 because r vector does not have any qj dots. Okay, and this partial derivative with respect to t, dou by dou t, does not introduce any new qj dot in it, so that term is 0. Right? Now what is this term? As I said, I am using Einstein summation convention, so there is indeed a summation over k here. Okay, there is indeed a summation over k, which is implied here. We are using Einstein summation convention. So what's this? You are summing this over all the values of k. Alright, but we know that for only one value this will be non-zero, only for that value where k is equal to j. Alright, if k is not equal to j, actually we have to take all the terms in this summation from k equal to 1 to n. Okay, but the only non-zero contribution comes from the term corresponding to k equal to j. Okay, which means that only if you have dou qj here, okay, dou by dou qj here, you will have 1. Alright, dou by dou qj means, so this, if you are taking, for example, if this j is, let's say, 3, okay, suppose this j is 3, right, then over all this coordinates, if you take this, you will get non-zero value only for k equal to 3. All other terms are 0. Right, so generally we can say that dou r vector by dou qk delta jk is simply equal to dou r vector by dou qj. Okay, this is a nice property of Kronecker delta. If you sum over, which includes the Kronecker delta, the summation is gone and the Kronecker delta disappears, and you can simply put k equal to j. Okay, that's a nice property. Right, that's why, so this is exactly what we wanted to show. We wanted to show that dou r vector by dou qj is equal to dou ri vector dot divided by dou qj dot. Alright, that's the result we have used here. Dou ri by dou qj is equal to dou ri dot by dou qj dot. Okay, this is a thing that we will be using time to time without much explanations. Okay, so I wanted to explain this because we will be using this Kronecker delta now and then, and this particular property. Alright, if you sum over something like this, or generally, okay, if you have some object with index k, okay, let's say summation over I, right, so we have some object with an index fi, okay, delta I j. Okay, this means that you are summing all over I. Okay, but the only non-zero term is when I is equal to j. So in this whole summation, the only non-zero term is I is equal to j. So you can put I equal to j and the summation disappears. Alright, so this simply you can write as fj. Okay, this is a property, it's a nice property of the Kronecker delta. Okay, alright, so yeah, I wanted to explain this because this Kronecker delta will be using. Stokes law we have seen. Okay. Now coming back to friction. So when we solve problems, it's good to know something more about friction. Right? So there are generally two kinds of friction, at least we can call them as kinetic and static friction. Okay, there are other frictions, but we are discussing kinetic and static friction here. So friction is the force parallel to a surface that a surface applies to an object. Alright, so an object is moving in a plane like this. Alright, so there is a force acting on the object. We are all familiar with this frictional force. Alright, and we can generally call this kinetic and static friction. What's kinetic friction? Kinetic friction deals with two objects moving relative to each other. Alright, there's a kinetic friction, which means that if there's a ball moving on a board like this, or a billiard ball or a carom coin moving on the board like this, there's a relative motion between this plane and the object. Okay, in that case the friction is called kinetic friction. Okay, and usually it's a good approximation. We'll use this approximation always to say that the kinetic friction between two objects is proportional to the normal force between them. Right, so there's a normal force exerted by this board on this carom coin or a billiard ball, whatever that we are talking about. Okay, there's a normal force, and generally we can write, or normally it's a good approximation to say that the force of friction is proportional to a normal force. Alright, so the coefficient of proportionality is called the coefficient of kinetic friction. Okay, we'll call it mu k. Alright, so mu k generally depends. It's something that has to be supplied as part of the problem. You need to know what's the coefficient of friction, and if you know the normal force, you can write down the kinetic friction, okay, the force due to kinetic friction. Okay, so F is equal to mu k n. You can write it as a vector, alright, where n is the normal force. Alright, generally this could be different for each component. Alright, this could be different for each component. Okay. So this k subscript here means that it's the kinetic coefficient of kinetic friction. Okay. Now let's go to static friction. Static frictions, if two objects are at rest, we say that there is a static friction. So in this case, we can only write an inequality. We can say that the friction force, the frictional force is less than or equal to this thing. All right. So this is the coefficient of static friction. This is the normal force. We can only say it's less than or equal to mu s n, which means that if it starts moving, okay, it may attain the maximum, and then there will be an equality. All right. So before solving the problem, the only thing we can say is that the static friction force has a maximum value equal to F max equal to mu s n. So just before the movement starts, you will get the maximum value for static friction. All right. So then we can only say the maximum value is this thing. Right. We cannot write exactly generally as in the case of kinetic friction. Let's solve a small problem. A particle is in contact with a rough horizontal board. The coefficients of friction for the motion in the x direction is mu x. So as I said, it's different in two directions. All right, it's mu y in y direction. If the normal force acting on the board is given by r, find the generalized forces q r and q theta. All right. So of course, you can find generalized forces using the general formula dou f vector dot dou r vector by dou qj. Okay, you could do that. Okay, that would give you qj. Okay, but you'll see that it involves more steps. All right, here we can solve it in a slightly easier fashion. That's what we'll do here. Of course, you can try this method also. Okay. So the frictional force in the x and y directions are mu xr and mu yr. Right? So now we look at the work done. Okay? The work done due to the frictional force. So we are assuming that it's kinetic friction. We are assuming that it's a kinetic friction, and the work done we can write as delta w is equal to mu xr delta x minus mu yr delta y. Okay, mu xr and mu yr are the components of frictional force along x and y direction. Delta x, minus mu xr and minus mu yr. Right. So the work done, okay, since the force is acting opposite to displacement, we can write it as mu xr delta x with a minus sign minus mu yr delta y. Okay, delta x is a small displacement along the x direction, and delta y is a displacement along y direction. Okay. Now in polar coordinates, we know that x equal to r cos theta and y is equal to r sin theta. These are the transformation equations. Right. So x equal to r cos theta and y is equal to r sin theta. Okay. Now we substitute here. Okay, we just substitute here with x equal to r cos theta and y equal to r sin. This is an easy way to do it because the x and y appear only here. All right. So we can write this as minus mu x r. What's delta x? Okay, what's delta x? Delta x equal to delta r cos theta. Okay. So you have to treat it as a product. You have to use a product rule here, and then we have r minus sin theta delta theta. Am I right? Because the derivative of cos theta is minus sin theta, and correspondingly there is a delta theta. Okay, so you can write as minus mu x r delta r. Okay, we can write as minus mu x r. Instead of delta x, it's delta r cos theta minus r sin theta delta theta. Okay, similarly you can do for delta y. Delta y will be equal to delta r sin theta plus r sin theta, r cos theta delta theta. That's what I have written here. Okay, I have started with the expression for work done. Okay, and I have translated delta x and delta y in terms of the polar coordinates. All right, plane polar coordinates. Okay, which means that I have used this transformation equation and I get this term. Okay. Now we can combine the terms delta r, coefficients of delta r and delta theta separately. Okay. that gives you, you see that it's minus mu r cos theta. So this, I hope you understand this. So this delta r, we can write this as delta r, okay, minus mu r cos theta, minus mu r cos theta. There's a delta here also, okay. So minus, this is mu x here, mu y r sin theta, okay. Is that it? Yes, delta r plus delta theta multiplied by, what do we have here, minus those mu x minus mu x r, those minus and minus, so it becomes a plus here, mu x r, right, mu x r sin theta. There's a delta theta here also, minus mu y r cos theta. There's an r sin, there's an r there, I missed that r there. Here also there must be an r. No, that's correct. That's correct. Here also there's an r. That's correct. Alright, so we have done it. Mu y r sin theta. Delta r. Yeah, that's correct. Okay. So now if we can say that the generalized force, okay, we know that the generalized force, you can write the work done like this, delta w is equal to qr delta r plus q theta delta theta. Okay. So we said that this qr, q theta, etc. need not have the dimensions of force, okay, generally, but this thing will always have the dimensions of work done. Okay, qr delta will have a dimension of work done, and q theta delta theta also will have a dimension of work done. Okay, that's why we can write delta w is equal to qr delta r plus q theta delta theta. Now we compare this with this thing, qr delta r plus q theta delta. So the coefficient of delta r has to be qr and the coefficient of delta theta has to be q theta. Okay, that's how we identify the answer here. qr is the coefficient of delta r in dw, okay, and you also have a coefficient of delta theta that gives you q theta. These are the generalized frictional force or components of generalized frictional force. Okay, so we have used a simple solution here. Of course, you can try the other method. Okay, of course, you can try the other method. Qj is equal to f vector dot dou r vector by dou qj. Okay, you can try this method also. Maybe I'll leave it to you as a homework, and you will see that this method is actually much easier. It saves us some time. Okay. So with that, I think we come to the end of this session, and we have practically completed the Lagrangian dynamics part, or specifically Lagrangian dynamics part. Of course, we'll be coming back to the concepts that we discussed in this session. Right? Now we are ready to move on to, let's say, different formalisms or different ways of formalizing classical mechanics. Okay, we'll do the Hamilton formalism, and maybe we'll go theoretically to Hamilton-Jacobi, and in between we have got some interesting things as Poisson brackets and canonical transformations, etc. So we'll go to these things now. Okay, now, so yeah, I think we'll put an end to, we'll conclude the Lagrangian dynamics part with this, and in the next session let's go on to the Hamiltonian dynamics. Okay, all right, thank you for now. We'll see you in the next session.